So we've got the area between 2 cosine x and x squared minus 1. And right off the bat, we'll notice that just like the one we did at the end of class last time, we're not given like limits of where this starts and ends. So we're really just looking for a specific region that's enclosed by these two functions. And we'll notice that if we try to set them equal to each other to try and figure out where they intersect, this equation is going to be a little bit difficult for us to solve, right? 2 cosine x equals x squared minus 1. We're not going to get any real nice values for that. Would you all agree with that?
Yeah.
Yeah. So one of the things that I'm going to put some videos up of is how to use your calculator, your graphing calculator, to find these points of intersection. But for today, we're just going to go and use the Desmos calculator online to just get some approximations for this. So if I graph 2 cosine x, and I graph, what was the other one, x squared minus 1, right? We should note that they are intersecting at negative 1.265 and positive 1.265 about. Yeah. And we would also be able to see really easily from the graph that the cosine function is the one that is above the other function, above x squared minus 1 on that interval. So we have two options here. And the first option we have is we can just integrate from negative 1.265 to positive 1.265 of our upper function minus our lower function. So we're going to do that first. I guess I need to go back to this one, right? So we're going to go from negative 1.265 to positive 1.265. And like we said, our upper function was 2 cosine x and our lower function was x squared minus 1 dx. And make sure that if you're subtracting a second function from your first one, and make sure you distribute that minus sign through to everything if you're going to rewrite this out. And so I'll do that right here. And I'm sure you can imagine that you're not really going to have a very good time evaluating this integral. Once you take the integral, right? Integral is not hard to find. It's 2 sine x minus x cubed over 3 plus x. That's easy to find, but evaluating that at negative 1.265 and positive 1.265 is going to be a little bit of a pain. You're going to have to just use a calculator to do that. And so anytime that that's the case, where these points of intersection have to be found using a calculator, you're welcome to just use your calculator to evaluate the value of this integral. So you guys all remember how I showed you how to do that previously?
Yeah.
Yeah, so math, option 9, and then go ahead and plug it in. And be extra careful that since this has a trig function and you have to be in radians. If you're in degrees, you're going to get a horribly wrong answer. So somebody go through, evaluate that integral, and tell me what you get.
$4.995.
Anytime we're doing a calculator problem on the AP test, we'll always round to at least 3 decimals. You can go further than that, but unless it specifies something different, go to at least 3. So we'd say that's 4.995 units squared. Good or no? Everybody okay with that? Other people got that same value?
Yeah. Yes.
Cool. All right, so one other thing I wanted to just mention about this is, what do we notice about both of these functions? Anybody notice anything similar about the two functions? Something they have in common?
They both have a line of symmetry.
Yeah, they both have a line of symmetry, and in fact, that line of symmetry is the y-axis, right? They're both symmetric across the y-axis. They're both even functions, right? Even functions are symmetric across the y-axis. So anytime you are looking for the area of the region that stretches from the same value on the left to the same value on the right, just positive and negative, of an even function, you know that both sides are going to come out to be exactly the same. So if we wanted to, we could have gone and done 2 times the integral from 0 to 1.265 of the same, 2 cosine x minus the x squared minus 1. And sometimes that will make arithmetic a lot easier if you're doing it by hand, not with calculator. With calculator, it doesn't really matter. But if you're doing it by hand, that might make life a lot easier, because a lot of the time, that 0 is very, very easy to evaluate. So we could have also done this, and you would have found, I don't know if we were S there instead of X, but you would find that would come out to be the exact same value as what we got here. So just something to maybe keep an eye out for and look out for. Okay. Definitely helpful. Good or no?
Good.
Sorry, why does this get you the same answer as the first one?
Because these are both, I'm going to go back to the graph, these are both even functions. And so they're both symmetric across the line the line x equals 0 across the y-axis. So this portion over here is identical to this portion over here. Since we're going from the same, from the negative 1.265 to positive 1.265, we can just take the half of it from 0 to 1.265 and double it.
Okay, thank you.
Mm-hmm. Everybody good with that now? All right. Okay, let's take a look at another one. This is a fun one here. So we're going to look for the area of the region that's in the first quadrant. It's bounded above by y equals root x. So there's y equals root x. Below by the x-axis. So this is a bound on it. So we're not going down into the fourth quadrant, which was obvious because it said first quadrant. And also the line y equals x minus 2, which looks about like that. Okay. And we're looking for this region right there. So what makes this one a little bit more difficult than the previous ones we've been doing? Nobody? All right, well, how would you go about doing this one? Any thoughts? We probably need to figure out what this point of intersection is, wouldn't we? Where does root x intersect with x minus 2? At what x value?
X squared minus 4x plus 4.
Okay, I mean, right, but what is the, okay, we can go through, and I guess if we want to, we can go through and solve this. X squared minus 4x plus 4, square both sides, right? And then you end up with x squared minus 3x plus 4 equals 0, or what else?
Wait,
I mean, it should be really easy for us to just see what this value is, then. We can go through and we can solve these equations. Sorry, I should have said minus 5x there, but
4.
Yeah, I mean, with any luck, you just notice that the value there is x equals 4, right? This becomes x minus 4x plus, or sorry, x minus 4x minus 1, and you get x equals 4. And x equals 1. And because you squared both sides of it, one of those is an extraneous solution, and that's the x equals 1. Only 4 makes sense in there, right? Because we have to have a negative square root for the 1 to make sense, but we don't have that. But hopefully we wouldn't have had to go through all that. We could have just seen that if we plugged in 4 there, square root of 4 is 2, and 4 minus 2 is 2. So that's important. We're going to need to find that. But in this previous one, we had to add the graph over here, right? The entire section of this region right here, from negative 1.265 to 1.265, 2 cosine x was always above x squared minus 1, wasn't it?
Yeah.
Yeah. But in this one, I don't always have the bottom of my region as y equals x minus 2. The top of my region is always the square root of x. But the bottom of my region is sometimes the line y equals 0, right? Sometimes it's the x-axis, and sometimes it's the line y equals x minus 2. You guys see the difference there? So if I were to try to integrate the square root of x minus x minus 2 from 0 to 4, that would also give me this area right here, which I don't want. Correct?
Yeah.
Yeah. So that's a problem. So what do you think we need to do? There's a few different things we can do, but what do we want to do? What's one thing?
You could find the x-intercept and then do the integral from there.
Okay, so x minus 2 equals 0 when x is 2. That's pretty easy to find, right? So how would I get this whole region then? I'd have to split this into 2 different integrals. One from 0 to 2 of what function?
Root x.
Root x. And I don't need to subtract anything from that, right? Because I'm just going all the way down to the x-axis. And I'd have to add to that an integral from 2 to 4 of the upper function, root x, minus the lower function, which is x minus 2. So I'll just distribute that minus sign all in one step there. And we get this. You all agree with that?
Yeah.
Okay. So let's evaluate this. So that's the integral of root x. That's x to the 1/2, right? So that becomes 2/3 x to the 3/2 from 0 to 2. And then we'll add to that 2/3 x to the 3/2 minus x squared over 2 and plus 2x. And we'll have to do that one from 2 to 4. Everybody good with that?
Yeah.
Okay. So now the fun part, right? We got to evaluate all this crap out. So 2/3 of 2 to the 3/2. Well, I'm just going to write 2/3 of 2 to the 3/2 minus 0, right? And then plus, what about this one? 2/3 of 4 to the 3/2. What's 4 to the 3/2? The square root of 4 is 2, and then cubed is 8. Times the 2/3 would be 16/3. And then minus 16 over 2, which is 8, and then plus 8 for the 2 times 4. And then we'll subtract this when we evaluated it 2, which is 2/3 of 2 to the 3/2, minus 2 squared is 4 over 2 is 2, plus 2 times 2 is 4. Everybody good with all that? And what do we have? We have 2/3 2 to the 3/2, and we have a minus 2/3 2 to the 3/2. So those will cancel. That's nice. So we're just left with a 16/3 minus an 8 plus an 8. Those will cancel. Minus a negative 2, so that's plus 2, and minus 4, right? So what's 16/3 plus 2 minus 4? That's 16/3 minus 2, which is what?
10/3.
10/3. And that was not absolutely horrible, but it was a little unpleasant, probably. But we'll note that gave us this region in green that we wanted, and we had to split it into 2 integrals from 0 to 2 and 2 to 4 because there was a different function bounding my region on the bottom. So anytime there's a different region on the bottom, you got to split it. Or if there's a different function bounds the bottom, you have to split it. Or if a different function bounds the top, you have to split it. Right? I could have a situation where I instead of saying it being root x the whole time, I could say it's root x from 0 to 2, but then it's x minus 2 from 2 to, or not x minus 2, but what would that be? Negative x plus 4 from 2 to 4, or something like that. But that's another point altogether. Everybody good with that?
Yep.
All right. Now, I don't think I really like that way, though. I think we should do this problem again. What do you guys think? Let's do the same problem. Here's root x. Here's x minus 2. Neither of those look very good. Let's try that again. Root x, x minus 2. Better. All right, we still want this same region here. But this time, I don't want to do 2 integrals. I just want to do 1. What if I did this integral, the integral from 0, different color here. I did the integral from 0 to 4 of root x minus our x minus 2. What would that give me? What would I have to also color in here?
The part below the x-axis.
Right, I'd
0 to 2.
also have to include that section down here, right? So that would be giving me this. Well, that's fine, as long as I subtract away whatever this is, right? And this should be very easy to find. Isn't this just a triangle? What's the area of this triangle? It's 1/2 the base times the height, right? Well, we knew this point was 2, so the base is 2. And what about the height? If this is y equals x minus 2, this is negative 2 down here, so the height is also 2. Do you guys agree with that?
Yeah.
So we could have done it like this. Yeah? Same integral. Let's do this integral. This is 2/3 x to the 3/2 minus x squared over 2 plus 2x from 0 to 4 minus 2. And what's 2/3 of 4 to the 3/2? We did that earlier, right? The square root of 4 is 2, cubed is 8, that's 16/3. Minus what? 8 plus 8. And what do I get if I plug 0 into all 3 of these? They're all zeros. So we've got 16/3 minus 8 plus 8 minus 2, which is 16/3 minus 2, which is again 10/3. Good or no?
Yeah.
Yeah. You guys like that better?
A lot better.
Yeah, sometimes you can find a nice, easy little trick. Nothing wrong with doing it the way we first did it. A lot more nasty arithmetic. Works out, get the same answer, right? But sometimes you can find a little trick using geometry. All right, now, you guys like that way better, right? I'd prefer not to do it that way, though. That way seems way too difficult. So here's root x, and here's x minus 2. And I'm looking for this region right here. Right? True?
True.
But this time, I want to do this integral, the integral from 0 to 4 of just root x dx. What's that going to give me? Won't that include this section right here?
Yes.
Which is just a triangle, isn't it? That's 2 and that's 4. And if this is square root of x, this height here has to be 2. So couldn't I do the integral from 0 to 4 of root x, which gives me the whole region underneath that curve, and then subtract the area of this little blue triangle? Seems like that would give me the same, I hope that would give me the same area. All right, so let's see here. Integral of root x, I would have done that a bunch of times, right? That's 2/3 x to the 3/2 from 0 to 4 minus 2. And well, we've done this a bunch of times, right? 4 to the 2/3 is square root of 4 is 2, cubed is 8, 8 times 2 is 16 over 3, minus the 0, when you plug in 0, minus 2. And what's 16/3 minus 2? It's still 10/3. So another nice, easy way to do this integral. Lots of different ways we could do this integral, huh? Pretty cool, isn't it?
Yes.
I can tell you're all very impressed. All right. Now, I liked that way. That's the way I would probably do this integral if I were doing this problem. But just for the heck of it, here's root x. Here's x minus 2. And I want to do this a completely different way now. So what we've looked at before was we were looking at which function was above the other one, right? That's what we did here. Which function was above the other one? That's what we did when we did this cosine one, right? Which function was above the other one? We integrated from the upper one minus the lower one. True? That's what we've always been doing with these, looking for the function that's above the other one.
True.
All right. Integration for area can also be done in terms of y. And that's what we're going to do now. We're going to do this in terms of y, which means we are looking for the rightmost function minus the leftmost function. And we are going to integrate using y values. So, which function for every y value from 0 up to here? What's the y value up here? X is 4. What's y?
2.
2. So from 0 to 2, which function is to the right of the other function? So pick a y value, like 1, let's say. Which function is to the right?
X minus 2.
Right. Pick another number, like 0.01. Which function is to the right of the other one?
X minus 2.
Pick some number like 1.999. Which function is to the right of the other function? Still x minus 2, right? The linear function here in this case is always to the right of the root function. Would you all agree?
Yes.
Okay. So what we're going to do is we're going to turn each of those, y equals x minus 2 and y equals root x, into terms of y. So we're going to solve for x. X is equal to y plus 2, right? If y is x minus 2, x is y plus 2. And if y is root x, x is equal to y squared. Everyone would agree there?
Yeah.
Okay. So like we said, the linear one is to the right. So we're going to do rightmost, y plus 2, minus the leftmost, which is x equals y squared, dy. And what had this better come out to give us?
10/3.
It sure as heck better give us 10/3. Integral of y is y squared over 2. Integral of 2 is 2y. Integral of y minus y squared is minus y cubed over 3. And we'll integrate from 0 to 2. Plug in 2, you got 2 squared is 4 over 2 is 2. Plus 4, that's 6. And then minus 2 cubed over 3, so minus 8/3. And then the second part of this is 0 plus 0 minus 0, right? Minus 0 plus 0 minus 0. So we got 6 minus 8/3. And 6 is, I believe, 18/3, right? And 18/3 minus 8/3 comes out to be 10/3. So we want to be able to integrate in terms of y also. And so this is just kind of a nice simple example for how we would integrate in terms of y. Put both functions in terms of y, x equals some function in terms of y, then take the rightmost function minus the leftmost function, and do your limits of integration as the lowest y value to the highest y value. Everybody good there?
Yeah.
All right. Now this was a great way to do this problem, but no, I'm just kidding. We'll move on to the next one. Oh, this is the same one that I have written because I was going to have it written there again. All right, let's do this. We want the area of the region enclosed by y equals x cubed and x equals y squared minus 2. So what do you think we should do first?
Look at the graph.
Yeah, let's look at the graph. Good idea. All right, we should know what y equals x cubed looks like. So we should also know what x equals y squared minus 2 looks like because we've taken other math classes before, but let's graph them. There's x cubed, right? And what was the other one? X equals, what was it? Y squared minus 2. So we're looking at this. And we want the region enclosed between the two of them. And just so that I can, we're gonna do something real quick here. We're just gonna put that graph over here so that I can draw all over it if I want to. I'm back on the lecture notes screen, right?
Yeah.
Okay, cool. All right, so there's our graph. And what do we notice about this? Is there one function that is always the upper bound of the region? And is there always one function that is always the lower bound of the region? The upper bound always seems to be for every x value from -2 over to whatever that intersection point is that we'll have to figure out here in a second. For all of these values, the upper part of the region is always defined by x equals y squared minus 2, isn't it? But the lower part of the region is sometimes defined by x equals y squared minus 2, and it is sometimes defined by y equals x cubed. You guys see that? That from -2 to -1, this defines the bottom of the region. And from -1 to 1 point whatever, the cubic function defines the bottom of the region. Good or no?
Yeah.
Okay. So that creates a little bit of an issue because that means we either have to split it here at -1 and find a way to deal with this, which is possible. And it's not inherently super difficult. Or we can look and see if there's always one function that is to the right of the other function. And so if I look at any y value between, I don't know, whatever that is, and whatever that is, and if I look at whatever y value I want, I think those must be like the square root of 2 probably. Take any of those, which function is to the right here at 1, let's say. My cubic is to the right of the parabola, right? Pick another one in here, like, you know, y equals -1/2. The cubic is to the right of the parabola, true? For every value between, sorry, not from this -√2, but from this -1 all the way up to whatever this y value is, the cubic is always to the right of the parabola. Would you all agree?
Yes.
All right, so we're going to try and do this in terms of y, and we're going to do the cubic minus the parabola, and we're going to do it all in terms of y. So first thing we need is the upper and the lower limit. The lowest this region goes is down to -1. And the highest this region goes is whatever that intersection point was. So if we go back here and look, that intersection point was y equals 1.793, right? So we'll go and plug that in here, 1.793. And the rightmost function, like we said, is the cubic, which is y equals x cubed, but I need that in terms of y. So that would be x equals the cube root of y. And then we will subtract the parabolic function, the one that's to the left, which is y squared minus 2. So I'll distribute the minus sign through and put a dy. And integrating cube root of y minus y squared over, or minus y squared plus 2 is not too difficult, but evaluating it at 1.793 is going to be a bit of a pain. So I'll let you guys use a calculator to find that value. And when you use your calculator, you just type in x's. It doesn't really matter what variable you use, just type in an x.
Why don't you need to do plus or minus the cube root of y when you rearrange it?
Because the cube root of y is not like a it's not like a parabolic function, right? Cube root of y can be both positive and negative, right? If we plug in a positive y value, the cube root is positive. If you plug in a negative value, the cube root is negative. You don't get one, or you don't get two different values potentially out of a cube root. You always only get one.
Okay, yeah. Thank you.
And technically, you get three, but two of them are complex values in the imaginary plane. So we don't need to worry about those ones. Just in the interest of me being accurate about what you get. Only when you do even roots do you have to take into account that positive or negative.
$4.215 maybe.
Maybe, I don't know, I haven't done it, so. Somebody else agree with that?
Yeah.
Cool. Very good. Any questions or issues with that, doing it in terms of y? All right, let's do a couple more problems. So this one we're not going to do in terms of y, most likely, since we've got y equals 2x squared plus 10, y equals 4x plus 16, and we're given some regions. Should we take a look at the graph?
Why not?
All right. I believe we had, what, 2x squared plus 10 was one of them, is that right?
Yeah.
And the other one was, what was it? 4x plus 16 or something like that?
Correct.
And we're going from where to where?
-2 to 5.
-2 to 5. All right. So let's go up here and look. We'll note that 4x plus 16 is above the x-axis at -2, right? And then in fact, they're both above the x-axis all the way from -2 to +5. Is that what it was?
Yeah.
Yeah. But in some portions of this, the parabola is above the linear piece, and in some pieces of it, the linear piece is above the parabola. Right, so we really need to figure out where do these things intersect. We can set them equal to each other to figure that out, but since we're using Desmos right now anyway, we can see that they intersect at -1 and +3. So I'm gonna go back here and I'm just gonna draw a really cursory sketch of this. And that was really not very good there. That's better. And we know that from -2, they got that there, they intersected at -1, they intersected at 3, and here's 5. And so we need to separate this into how many different integrals?
3.
Exactly. The first one should be an integral from where to where?
-2 to -1.
And which function should be above the other one? Or which one is above the other one on that integral?
2x squared plus 10.
Right, 2x squared plus 10 minus 4x plus 16, so minus 4x minus 16 dx. And then we need to add to that an integral from -1 to the next intersection point, 3. And now it'll be 4x plus 16 minus the 2x squared and minus the 10. That sort of looks like a 10. We'll pretend it does. And then the last one should be 3 to 5. And again, we got to flip back to 2x squared plus 10 minus 4x minus 16. Good or no?
Good.
All right. And I don't know, I feel like you guys don't need me to teach you how to do arithmetic, and those are such simple integrals that we could probably call that good and just say this is the appropriate setup. If this was on the AP test, you'd want to make sure that you showed, if this was a non-calculator or a calculator question, show how you got x equals -1 and x equals 3 is the intersection points. And so if this was a calculator question, just writing the equation and then writing these points is good enough. If this was a non-calculator question, you'd have to actually solve that quadratic, which is, you know, not that hard to do, right? Just subtract the 4x and the 16, divide it by 2 and factor, and then you're good. Good or no?
Good.
All right. Let's do one last problem for this quarter. So we want the area of the regions enclosed by sine x, cosine x, x equals 0, and x equals pi over 2. Sine x, cosine x, x equals 0, and x equals pi over 2. Pi over 2 is when my sine function hits its max and my cosine function hits the x-axis, right? Hits its x-intercept. So we're looking at this plus this. And so this really should technically be two different integrals, right? It should be an integral from 0 to, where do they intersect? Where does sine x equal cosine x?
Pi fourths.
Yep, pi over 4. So we'll integrate from 0 to pi over 4. Which function is above the other one from 0 to pi over 4?
Cosine.
Cosine x minus sine x. And we'll add to that an integral from pi over 4 to pi over 2. And now sine is above cosine for that interval. And we integrate. And we'll do this integration. What's the integral of cosine x?
Sine.
Sine x. And what's the integral of negative sine?
Positive
Sine.
cosine.
Positive cosine. And that needs to be evaluated from 0 to pi over 4. And then over here, what's the integral of positive sine?
Negative cosine.
Negative cosine. And the integral of negative cosine?
Negative sine.
Negative sine. And this one is from pi over 4 to pi over 2. Sine of pi over 4 is root 2 over 2. Cosine of pi over 4 is also root 2 over 2. Minus sine of 0 is 0. Cosine of 0 is 1. And we'll add to that negative cosine pi over 2. Well, cosine of pi over 2 is 0, right? So that's just 0. minus the sine of pi over 2. What's the sine of pi over 2?
1.
1. So we got 0 minus 1, and then minus negative cosine of pi over 4, which is negative root 2 over 2, and then minus sine pi over 4, which is another minus root 2 over 2. And let's see, root 2 over 2 plus root 2 over 2 is 2 root 2 over 2s, or just root 2. So we got root 2 minus 1. We got another minus 1 here. And then we've got plus in front of all of this. So this minus distributes to both of those. That's another root, it's a positive root 2 over 2 plus another root 2 over 2 when I distribute the minus sign through. So that's just another root 2. And we end up with 2 root 2 minus 2 units squared. Good or no?
Yeah.
Cool. Any questions on anything we've done in the last 9 weeks or today?
Can you go back to the last problem for a minute?
Sure.
Thank you. I don't understand. Like it said find between -2 and 5, right?
Uh-huh.
But they intersect at -1 and 3 or something.
Yep. So that means we're looking for the area of this region, because that's still between them, from -2
Okay,
to
thank you.
-1, plus this region, plus this region.
Thanks.
No problem. Anybody else? Any other questions from today or life in general? This class, math?